Hello, everyone. This lecture is the last lecture of our entire semester. And in this lecture, I'm going to summarize cycles that we have learned so far. And I'm going to talk about life lessons that we can take away from thermodynamics class.
The first thing that we want to review is about how we can apply the first law and second law to the cycle entirely. Okay, so please look at the diagram that I gave you about the cycle, where we have a cycle in the middle of the high temperature reservoir at TH and low temperature reservoir at TL. So when you try to run a heat engine cycle, what you have to do is that we have to get certain amount of heat QH from a hot temperature reservoir. And from this heat, we can convert part of it to the net work W. Then the remaining part of heat should be rejected to the low temperature reservoir. So that is how we understand about the thermodynamic cycle operation. Many times, your low temperature reservoir is fixed at certain dead state or your environment, like a river, ocean, or lake. Okay? And we define that temperature of your surroundings, like your reservoir, as dead state temperature. So instead of using TL, many times we use T naught to define the dead state temperature. So, by understanding how the thermodynamic cycle is run between these two reservoirs, let's try to make your cycle as your system. Okay, then how can you apply the first law of thermodynamics to that cycle? Now, the first law of thermodynamics can be written as delta U equals to Q minus W. Okay, the change of your internal energy of your system is due to the heat transfer or work transfer. So if we apply that first law of thermodynamics to the cycle, now the characteristics of a cycle is that your first state should be the same as your last state, because that makes a cycle, right? Moving forward. By saying that, your change of your internal energy of the cycle should be 0. Right? Then by looking at your schematic diagram, we have two terms of heat, which is heat in QH and heat out, that is QL. And we have work out, that is W. So in order to make it clear, let me use W net. Okay, so then I'm going to write that as W net. So that is what we have. Okay. Or I can write that as QH minus QL should be equal to W net. So that is a result of applying the first law of thermodynamics for the cycle. Then how about the second law? The second law of thermodynamics can be written as delta S. The change of your system, change of the entropy of your system is due to the entropy transfer and plus entropy generation. Okay. So again, because the system is the cycle, the entropy change of the system should be 0. So now we have 0. And now we have two terms of energy, entropy transfer, which is due to QH and at TH minus QL divided by T. Now let me use T naught, which is the dead state temperature, and we have entropy generation. So from this equation, what you can see is QL, the amount of heat rejection, can be written as T naught over TH times QH plus T naught entropy generation. Now I have one equation that is from the first law of thermodynamics, and I have another equation that comes from the second law of thermodynamics, where we have QL as the common term. So what I'm going to do, or what I can do, is that I can insert the second law of thermodynamics equation to the position of QL in the first law of thermodynamics. And what I have is W net is QH minus T over TH times QH plus T naught SG. Then what I can rearrange is we have QH now and 1 minus T naught over TH plus and minus T naught SG. And if you look at this term, 1 minus T naught over TH, that is actually the thermal efficiency of the Carnot cycle. Okay? So please read the lecture note that I discussed the Carnot cycle. And from that lecture note, what I can see is the Carnot cycle efficiency. Okay, or many times I will use reversible efficiency, which is defined as reversible network divided by heat input that can be derived in terms of 1 minus T naught over TH. So that is your Carnot cycle, which is W net reversible divided by QH. Now, how we can interpret that equation is your net amount of work in real cycle, right, is actually smaller than the reversible work that can be understood from the first term, right? So now we have QH here, and this one is the reversible Carnot cycle efficiency and can be understood as the net amount of work for the reversible process divided by QH. So the first term tells us that is W net reversible, and we have additional term that is T naught SG. And we call that second term as the lost work. But many times we define that as irreversibility. Okay, and that is in symbol of I, and that is what we have. That is how we understand that. Okay. So when you try to run your thermodynamic cycle, okay, your actual net amount of work is always smaller than the Carnot work or reversible work. And the difference gives us how much work has been lost due to the irreversibility or entropy generation that resides in your cycle. Okay? So that is how we can calculate the irreversibility of the cycle. And I really hope that you understand now about how we understand the first law and second law of thermodynamics for entire cycle and how we get to those kind of conclusions. But many times, we have to apply the first law and second law of thermodynamics for each process of the cycle. Okay? Depending on your cycle, depending on your heat engine, sometimes you have to consider the heat engine as the closed system. And the good example is like Otto cycle or diesel cycle. And sometimes you have to consider your system as the open system. And that cycle includes the Brayton cycle and the Rankine cycle, and even the refrigeration cycle, vapor compression refrigeration cycle. So here the very important question is that how can we apply that first law and second law of thermodynamics for either closed system or open system to each process of the cycle? And depending on how you do it, then you can come up with the equation that you have to use to do the thermodynamic analysis of the cycle. Okay. So now one more thing that I have to emphasize here is that when you talk about the thermodynamic cycle analysis of heat engines, And even not only the heat engine, for in general thermodynamic cycles, you always have to focus on two aspects. One is what is the amount of power, okay? Or what is the amount of your desired output? So that is more about power output, that is more about cooling capacity or heating capacity, but that is one thing. And the second aspect that you have to always focus is that how efficient your cycle is. Okay, so it's all more about the efficiency for heat engines, or the coefficient of performance, or in short, COP, for the refrigeration cycle or heat pump cycle. Okay. Then let's take a look at the closed system first law and second law of thermodynamics, and that is what we see. And we already used those two equations in the last page, so I'm not going to talk a lot about it. When you consider open systems, though, those equations have slight changes because you have to allow mass transfer or mass flow into the system or control volume, or flow out of your control volume. So the first thing that you have to think about is that how can you balance the mass because of this flow? And when you think about the steady state condition, then now the mass balance can be written as the total amount of mass flow rate that comes into your control volume should be balanced as the total mass flow rate of flowing that goes out of your control volume. Okay, so that is what you have. The first law can be written as the second equation. Okay, many times in the cycle analysis, components only have one inlet and one outlet. It's not always true, but many components have only one inlet and only one outlet. So in that case, if you have only one inlet and only one outlet, then your first law of thermodynamics can be written as this, right? Or by dividing this equation with m dot, we have q minus small w plus hi minus he. And so that is how we can write the first law of thermodynamics for an open system. The second law is the same. Okay, so we can write up the second law of thermodynamics in mostly general case, but many times we only have one inlet and one outlet. Then this equation can be simplified as q dot over t plus m dot and si minus se plus entropy generation rate, so that equals to 0. Or we can write it as small q over t plus si minus se plus small sg equals to 0. In that case, unit should be joule or kilojoule per kilogram Kelvin. And the other one, the equation on the top is kilowatt per Kelvin in terms of unit. And for first law, you have kilowatt, or we have kilojoule per kilogram. You must write the unit, okay? Otherwise, a number doesn't mean anything. So always don't forget to write the unit when you write up your answer or when you write up your certain number. So that is the key important thing. Don't forget ever about that part. Okay, and also, conceptually, this basically talks about the same thing. Either we talk about closed system or open system, but be very careful when you try to write up the first law and second law of thermodynamics. Okay, because depending on your system, you probably should start from different form of equations. Okay, so that is another very important thing that you have to take away from this summary.